Alright, hello everyone, and today we're going to continue on with the substitution rule. So let's just start with an example here. So it'll be the integral of x cubed over the quantity 2x to the fourth plus 1 quantity squared, and then we have dx. Alright, so this example doesn't have any square roots. Usually that's what we let u equal. And so for now, you have to guess something for u. If you don't guess anything for u, you won't be able to solve these integrals. So keep that in mind. Right now, the thing that looks most complicated is this thing that's on the inside that's being squared. So let's let that be u. Okay? And then we look at our differential. So remember, that's du. We take the derivative, so 8x cubed, and then multiply by our differential dx. So then we look up at our integral and see that we do not have an 8x cubed dx. However, we have an 8x cubed dx for our du. So all we need to do is get rid of that 8 so we can move it on over to the other side. So we get 1/8 du equals x cubed dx. Alright, and that's exactly what we have there. So maybe I'll highlight that in a different color. So we got x cubed dx. Alright, so now what we're going to do is actually do the substitution. So what I have highlighted in yellow is what u is. So we got 1 over u squared when we do that substitution. And then the blue is exactly 1/8 du. Alright, so the 1/8 is just a coefficient, so we can take it out of the integral. And then we're left with 1 over u squared du. We can write that as u to some power and be able to take the antiderivative using the power rule. Okay, so we have that. We're going to add 1 to our exponent. So u just off to the side, -2 plus 1 gives you -1. So you got u to the -1, and then 1 over your new exponent, which is -1. Alright, and then we're going to have plus c. Now we're going to simplify this. So 1 over 8, and then we can bring u to the denominator, and then plus c. So to continue on, we have, well, we started with x's, we got to end with x's. So we have 1 over 8, and then whatever u was. So 2x to the fourth plus 1 plus c. And there we go. There's our antiderivative using a u substitution. And a nice example where we don't have a square root. Okay, next. All these integrals that we've done so far have been indefinite integrals. So there were no numbers attached to our integral sign. Let's try one now that has limits. So a definite integral. So let's go from 0 to 1. We're going to do 2 plus 3x cubed dx. Okay, now for these ones, there's two ways we can go about doing this. So the first way, so solution 1. What we're going to do is drop the limits, and then we're going to put them in at the end. So we're just going to treat it like the previous indefinite integrals that we've looked at, and then substitute in our limits of integration later. So here we have this integral. We see the thing that's making it complicated is this thing inside the parentheses. So we're going to let u equal that. And again, you have to just guess exactly what u is. And once we do that, you have to try and see if you actually get somewhere. Again, if you don't guess anything, you won't be able to solve the problem. So then we take our derivative, which is just 3, and then we have our differential dx. Okay, we look up at our integrand and see we do not have a 3 dx, so we're going to divide by 3. And so we get 1/3 du equals dx. And now we're able to substitute in. So continuing on, instead of the blue portion, we have u cubed. Instead of dx, we're going to have 1/3 du. And now the only variable is du, so that's great. We can integrate. And we have u cubed, so we can just do our power rule. So we add 1 to the exponent and then multiply by 1 over the new exponent and then plus c. So we get 1/12 u to the 4th plus c. We can substitute in for u and get 2 plus 3x to the 4th plus c. And there is if it was our indefinite integral. Now we have to continue on, remember, because we had limits on our integrand. So here's our original integral. We just found the antiderivative, and we know that that is, using the fundamental theorem of calculus, it is 1/12 times 2 plus 3x to the 4th, and then we have to evaluate it from 0 to 1. So we substitute in 1 first, and then subtract when we substitute in 0. Okay, then it's a matter of simplifying. Let's see, we got 5 to the 4th minus 1/12, 2 to the 4th, and that is 625 over 12 minus 16 over 12, which equals 609 over 12, and we can simplify the fraction to be 203 over 4. Okay, so this way you drop the limits of integration and continue on. And then at the end there, you have to put back your limits of integration and then do the fundamental theorem and get a complete answer. Now let's do solution number 2. And this is nice because either way you want to complete this, either way you'll get the same answer. So it's really a preference. So you start out with your original integral for the second way, and we're still going to let u equal that same thing. Alright, and then we take our differential, just like before, and then we move things around so we can get the dx by itself. Alright, so that's all the same. However, let's focus on these limits of integration. The 0 means that the smallest x value is 0. The 1 means that the biggest x value is 1. So what we have to do here is look at when x equals 0. And we want to figure out what u equals then. So we're substituting in x equals 0 into u. There we are, and we get that u is going to equal 2. So the smallest x value is 0, the smallest u value is 2. Then in the other extreme, where x equals 1, we have to find the u value. We get 2 plus 3 times 1, just substituting in 1 for x, and we get that u equals 5. So if we continue on with our integration, we can do the u substitution, where we get the integral of u cubed and then times 1/3 du. But now we're integrating with respect to u. So we need the smallest u value, which we just found was 2, and the biggest u value, which is 5. So keep in mind we had to change those limits of integration for this second solution because the x values, we're integrating with respect to x in the first integral, and then we're integrating with respect to u in the second. So the limits of integration must change. Alright, then we continue on. We take the 1/3 out, and we integrate. So that's u to the 4th times 1 to the 4th. And then using the fundamental theorem of calculus, we evaluate it from 2 to 5. So we can simplify that to be 1/12 again, u to the 4th, and we evaluate it from 2 to 5. 1/12, substitute in 5, and then subtract when you substitute in 2. Okay. And so again we get 5 to the 4th is 625, and then 2 to the 4th is 16. We subtract the 2 and get 609, just like before. And we can simplify the fraction to be 203 divided by 4. And so you can see in both solutions we get the same answer. Okay, we get the same answer. However, in the second way, we had to change the limits of integration. So keep that in mind whenever we have definite integrals. You can do it either way. It's just a matter of preference.